Hi, I'm Hao-Wei Chen from National Tsinghua University, Taiwan. Welcome to the presentation of pixel-wise prediction-based visual odometry via uncertainty estimation, which can be abbreviated as PWVO. In this work, we study mitigating the noises from the moving object for the visual odometry task. PWVO has two main contributions. First, we introduce the concept of pixel-wise prediction into the VO task, and combine with uncertainty estimation and corresponding selection module to deal with the noises induced by moving objects. Second, in order to validate the advantage of PWVO, we further develop a data generation workflow which generates data with high flexibility. This is the outline of today's topic. I will quickly give a brief background introduction about traditional and general learning-based VO. Then I will talk about the proposed payment method and data generation workflow. Finally, I will demonstrate the experimental results. VO is the process of determining the position and orientation of a robot or camera when it moves by analyzing the associated images. The figure demonstrates the architecture of general learning-based VO methods, which are referred as VONet. They take paired RGB image as input and use CN to extract the feature. They estimate the 6 degree of freedom camera pose by separately predicting the camera rotational angle and translational offset between two frames. Estimating VO from raw images often suffer from the existence of noises coming from moving objects. The total flow consists of both ego flow and object flow. Therefore, the correspondence extracted from those moving objects might not be directly related to the motion of camera viewpoint. This leads to degradation in accuracy when performing VO. Furthermore, because the absolute depth scale is unknown, which is well recognized as an ambiguity problem. This figure compares PWVO and the baseline VONet from the perspective of their saliency map, which highlight the pixels that contribute to the predictions. It can be observed that the highlighted pixel of VONet saliency map cover both the object regions and the background. In contrast, the highlighted pixel of PWVO saliency map only fall on the background. It confirms that PWVO is capable of effectively suppressing the influence of noises. On the other hand, the baseline VONet cannot. The proposed PWVO architecture, which consists of two stages, an encoding stage and a pixel-wise prediction stage. The encoding stage is responsible for extracting features from the input data. The pixel-wise prediction combined with uncertainty estimation can be formulated as distribution learning. The former is the mean and the latter is the variance. To reconstruct the equal flow, we need a global set of camera motion. We design a selection module to substitute the global average pooling layers. The selection module first split the entire pixel-wise predictions and uncertainty into patches, then find the lowest uncertainty value and the corresponding pixel index in each patch. These uncertainty values are fed into a softmax layer to obtain the weight of each patch for the local VO prediction. Finally, the global VO prediction is calculated by the weighted sum of the local VO prediction. Our loss consists of four parts. First and second are the rotation and translational losses, which are used to refine the pixel-wise based camera motion predictions. Third is the flow loss for the ego flow, which is reconstructed by the global estimated camera motion. The last one is depth loss, which is the other one distance between predicted depths and the ground truth depths. Combining these losses, we can train our network in an end-to-end fashion. Pipeline displays the data generation workflow. Based on the 5 distinct steps in the illustration, we can obtain the ego flow, object flow, and total flow. The workflow is developed to be fully configurable with an aim to provide diverse combinations of motion of the camera and the moving objects. We train PWVO on the dataset generated by the proposed data generation workflow and evaluate the trained PWVO on the validation set of the Tinto dataset. We compare our PWVO with three baseline methods. First one is VONet. Second one is VONet with a pending attention layer before predicting the camera motion. Third one is the PWVO without selection module. We evaluate the method in terms of endpoint error and L1 error of the predicted camera motion and the ground truth camera motion. In the table, we can observe that the PWVO outperforms the other baseline method. The naive PWVO without selection module degrades the performance by a large margin, which represents the effectiveness of the design of the selection module. The figure represents several examples for demonstrating the qualitative of PWVO on the Tinto validation set. It can be observed that the predict ego and the object flow maps align closely with the ground truth annotation, and the estimated uncertainty maps are highly correlated with the full arrow map of ego flow maps. In the shortcut, it can be observed that the uncertainty map is highly correlated with the arrow map of rotation and translation, which implies that the uncertainty map is able to capture the noise in the input observation. Thank you for your listening.